Hello, can you hear me?
Yes, yes, Professor Iryna, we can hear you.
I cannot hear you for some reason.
You cannot hear us?
Now I can hear you. Can you still hear me?
Yes, yes, we can. Yeah.
Great.
So we'll just start in a moment.
Shall I share my slides, or you have some slides before me?
Yeah, we'll just, you can share your slides and we'll just shortly introduce you for your talk.
All right, thank you.
So we'll start now. So dear all, welcome to the day 2 of the symposium. We have our next keynote speaker, Professor Iryna, who's joining us online from Germany. Professor Iryna is a professor of computer science and director of the Ubiquitous Knowledge Processing Lab at the Technical University of Darmstadt in Germany.
Sorry, the connection was interrupted. I could not hear you.
Okay. So, we have our next keynote speaker, Professor Iryna Gurevych, who is joining us online from Germany. She's a professor of computer science and director of the Ubiquitous Knowledge Processing Lab at the Technical University of Darmstadt in Germany. Her main research interests are in machine learning for large-scale language understanding and text semantics. Iryna's work has received numerous awards, for example, the ACL Fellow Award 2020 and the first ever Hessian Louis Distinguished Chair Award in 2021. Iryna is co-director of the NLP program within ILIS, a network of excellence in machine learning. She is currently the president of the ACL. In 2022, she has been awarded an ERC Advanced Grant. In today's talk, Iryna is going to talk about the application of NLP in the field of healthcare, especially mental health, titled NLP Meets Psychotherapy, from estimating depression severity to estimating the client's well-being. Thank you, Professor Iryna, for gracing this event. It is really an honor to have you here with us today. Over to you. Her network, I think, is stuck somewhere. Professor Iryna, can you hear us? Our network is fine, right? Yeah. 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 Yeah, she's back. Okay. Can you hear us, Professor Iryna?
I can hear you. There are some interruptions in connection. I'm actually not in Germany right now. I'm in a different country, and they promised a stable internet connection. So I'm a bit worried, but nevertheless, let us try our best. I'm sorry for the trouble. Good morning, everybody, and I'm delighted to give a talk, NLP Meets Psychotherapy. Depression is a very common and a serious problem. And globally, a huge number of people, millions of people, suffer from depression annually, and these numbers are rising quite quickly. This also leads to people's suffering and enormous economic losses, and the numbers are really pandemic. And we know that a lot of depression and mental health disease is even unnoticed and untreated, so the real numbers are higher than what I show here. So mental problems are common and serious, and yet most people who suffer from mental health issues are not aware of the fact that they can receive help and that the way they feel is not their own fault. They do not seek treatment, and they are not diagnosed. And when they come to seek treatment and mental health services, they are often too late and the disease can be not well treated, or they are not well assigned to the appropriate treatments. And though we do have many evidence-based psychological and pharmacological treatments for depression, the response rate remains quite low, about 50%, meaning that up to half of all patients do not benefit substantially from the treatment. And importantly, research also shows that there is a very high variability between different patients and between different therapists. So we need a lot more empirical evidence to improve the situation in this important medical area. However, the research in mental health depends on decades of old methodologies, such as self-reports, which are very subjective and may not reflect the real state of the patient. So they have critical shortcomings. And to tap what occurs within psychotherapy sessions, researchers have developed numerous observer coding schemes. However, this coding is extremely labor intensive and is also expensive to implement. And the studies have been usually conducted on small samples, so we don't know if they reflect the reality in large scale. In consequence, we need alternatives to the traditional way of doing research that can recognize the complexity of mental health issues and depression in particular, the heterogeneous nature of clients and the different options of therapeutic interventions. And one extremely promising way to overcome the shortcomings which I've talked about is to use AI and NLP techniques to analyze mental health data to identify individuals' risk of progressing to depression and predict what methods and therapies will work for which client. So instead of making clinical decisions based on trial and error, we want to shift the medicine towards evidence-based prevention with the help of technology and raise its precision to improve the situation. So some major shifts that currently happen in this field is that the psychiatry and clinical psychology try to move to more fine-grained profiles of the clients, including technological approaches, and also they try to move from general treatment models to more specific interventions and processes. The next trend is to move from self-reports to multimodal analysis and move from correlational analysis to more sophisticated data analysis models that can capture the heterogeneity of the clients and the complexity of the psychotherapy process. Next, they also try.
Iryna, would it be possible to maximize the slides? They're appearing kind of like narrowed down in the window. Right. Yeah, I think that'll be great. Thank you.
Okay. So did I fix the issue? Yes.
Yeah.
Okay. And finally, there is a process moving from one-person psychology to two-person psychology, where they try to find predictive features both in the behavior of client and the therapist, and how to match these two together to achieve optimal treatment. In this talk, I'm going to cover two projects that we currently conduct in the lab. So in the first, we use predicted client emotions and self-reported client emotions to measure emotional coherence. And in the second project, we estimate the severity of depression with the help of NLP in social media. First, let's start with the predicted client emotions. One primary objective in psychotherapy is to assist clients in aligning their emotional experience with the words that describe them. Many emotion theories suggest that when individuals are able to express their emotions in a way that matches their internal emotional state, the better they are able to communicate and handle their emotions. And in contrast, when individuals experience emotions but are unable to express them or express emotions inaccurately, without recognizing how they feel, their ability to adaptively communicate and handle their emotions is impaired. And according to these theories, emotional coherence, defined as the coordination between different emotional responses as the emotion unfolds over time, is considered crucial to the well-being of an individual. In the past, the scalability of psychotherapy research about this problem of emotional coherence was very limited, because this is based on manual analysis of small sample of data. And now the question in our project is, how can we scale this up with the help of AI and NLP? And in this project, we collaborate with clinical psychologists because we need expert annotations that require clinical expertise. And based on those, we want to provide NLP solutions to facilitate the study of psychotherapy processes at the dialogue and at the session level. According to these goals, our aim is to use state-of-the-art emotion recognition models in NLP and automatically label clients' emotions at the utterance level. And then we use this labeled data to examine the coherence between the verbally expressed emotions and self-reported emotions by the client. And finally, we examine the association between emotional coherence and the client's well-being. So we have these two components: emotional expression defined by verbal expressions from dialogues during psychotherapy sessions, and the emotional experience as recorded by client self-reports on emotion taken after each session. And the dependency between the two is the emotional coherence. And as I've explained, it is considered to be crucial for the success of the therapy based on emotion theories. And we try to decode this to a diagnostic value. Does emotional coherence have a correlation with clients' well-being? So our data set here is based on our collaboration with the clinical psychologist from the Bar Ilan University Psychotherapy Clinic, and it's called BIRU dataset. These are psychotherapy session dataset in Hebrew, containing about 900 sessions from 68 clients. And this is mostly about anxiety and affective disorders like depression. We have about 60 therapists, and the therapy was recorded over a time span of about 9 to 12 months. A part of this data was coded by experts. There were 2 experts, and we computed kappa statistics showing that the annotations of emotions are reliable. We have about 22,000 utterances and 4 emotion labels: positive, negative, mixed, and neutral. We also have the utterances of therapists, which are labeled by intervention labels, which are 8 different labels. However, in the project I specifically present today, or in the first part of the project, we only study the utterances by the clients, and we do not yet relate them to the interventions, which is subject of our ongoing work. And basically what we do here is based on this gold standard. We train a classifier for utterance level emotion labels, and then we scale this Can you hear me again?
Yes.
Yeah,
Yes.
yeah.
Yes.
Yeah, sorry, I have not noticed where you lost me. So I repeat the last slide. So we have session level metrics from the patient. We have the profile of mood states with the coarse-grained emotions, positive and negative. And we have the client's well-being measure, which is called Outcome Rating Scale, ORS. And this measure assesses the client's well-being, and the evaluations are done over different aspects of well-being, like individually, interpersonally, socially, and overall. So in our study, we first label the emotions individually on the level of utterances. This is Hebrew language, by the way, and we use at that time the Hebrew-based pre-trained language model Aleph BERT, which is trained on the gold data set, and we evaluate with F1 score and the Kappa scores. So then we measure the association of these emotion labels with self-reported emotion, in particular the POMS scale, and we aggregate the utterance level emotions to the session level, and we measure the association between the two measures. So once we have the association, which is emotional coherence, we then measure the association of emotional coherence and the outcome rating scale. This is our diagnostics tool because the outcome rating scale shows the client's well-being as per their self-assessment. So now I'd like to talk about the results. So in the NLP part, we use state-of-the-art techniques at that time, and we fine-tune Aleph Berta for this emotion recognition task and compare a couple of models. And here we have the state-of-the-art results with the Aleph Berta model, which is the best one for this task. And using this model, we then scale up to the whole data set. In our error analysis, we find errors typical of the sentiment analysis techniques. For example, I'm dying on my dad. He did it to me with good intentions. Is misrecognized as negative based on lexical cue. And in the second example, I did not have a good trip, but in the lab, everyone thought that I've enjoyed and had fun. Is mislabeled again because it cannot deal with a negation. And then we measure the correlation between our emotion labels and the client self-reported emotion labels. That is POMS, and we find that we have statistically significant correlation here. So our hypothesis is validated. If we have clients expressing their positive emotion, this positively correlates with their emotional self-assessment. And the second finding from this experience generated data. So that means that our NLP techniques provide a good help in scaling up the analysis and validating this on a large data set. And then in the final step, we measure the correlation between the emotional coherence and the well-being scale called ORS. And we find that the emotional coherence in positive emotions shows statistically significant correlation with the client's well-being. So in summary, our contributions are as follows. First of all, we scale up the utterance level emotion recognition in psychotherapy dialects, eliminating the need to label a large data set. And then it is the first study to our knowledge to examine emotional coherence between emotion expression and emotion experience. And it confirms the positive correlation between identical emotion groups, positive, positive, and negative, negative, and negative correlation across non-identical groups. We study emotional coherence in longitudinal data and how it unfolds across session. And we find diagnostic potential of studying emotional coherence when coupled with clients' well-being measures. That is why we confirm our hypothesis. And our results have several clinical implications. First, they highlight the importance of emotional coherence, particularly in positive emotions. Moreover, therapists are encouraged to identify clients or sessions characterized by a high dissociation between emotional experience and the verbal expression of emotions, and tailor their interventions to help clients express positive emotions verbally and increase their positive emotional awareness. And further, automatic emotion recognition models may be integrated with existing feedback systems to provide an indication of the levels of emotional coherence in psychotherapy sessions and allow therapists to modify their interventions and improve them. Obviously, this study has a couple of limitations, and there's a lot of potential ongoing future work. So in this study, we only verify our hypothesis in Hebrew language psychotherapy dialogues, and we study this on a limited data set. So we just have one data set, and of course, with the help of multilingual state-of-the-art techniques, we can scale up the study and also study cross-cultural dimensions of this phenomenon. And also, so far, our study is only based on text. However, we do have the multimodal recordings of the client-therapist conversations, and we are planning to use video and audio modalities in future, and also study the relation between text and these different modalities and see how can we improve our results. So now let me move to the second part of my talk, and this will be about estimating depression severity, and in particular, we leverage state-of-the-art semantic similarity techniques in order to solve this task. Here we work with social media, in particular the data sets available as part of e-risk track CLAF challenge. And the work before this work suffered from several challenges. So mostly depression severity estimation was formulated as a binary classification task, which is of course a very, very crude simplification of this real life problem. So we could differentiate between depressed and control users, but we don't have any scale for this, and any more sophisticated scale for this. And because of this, the capacity to prioritize users with higher risk is limited. So we want to have a more fine-grained scale. And second, many of the works used engineered features, and these features are more difficult to interpret than clinical markers, such as validated depression symptoms. And of course, deep learning models also limit the interpretability of the decisions, which is why in this work, we want to experiment with a semantic similarity approach. And we propose a pipeline which allows us to incorporate clinical questionnaires to detect the presence of symptom markers. In particular, we adhere to the Back Depression Inventory 2, which is a widely used scale in psychotherapeutic research, and it includes 21 recognized symptoms with 4 alternative responses. So basically, we built 21 different symptom classifiers. So an example of symptom is sadness with 4 options. I do not feel sad. I feel sad much of the time. I feel sad all of the time. And I'm so sad or unhappy that I can't stand it. So instead of just classifying the depression on a high level, for each symptom, we built a 4-way classifier. So our task is to estimate depression severity levels for social media users based on their writing history. the depression level is defined by this BDI-2 score, and this is a sum of all responses to each option, representing each of the 21 symptoms on this scale with 4 different options. Now, a couple of words about our data sets. As I've already mentioned, they stem from the freely available e-risk depression severity estimation task that was conducted in 3 years, 2019, 20, and 21. And we have different number of users here. As you see, the number of users is not particularly high. In the first year, we have 20, in the second 70, and in the last 80 users. And this is based on Reddit users. So we use Reddit data, and for this data, we have a writing history of each subject who participates in these experiments. And so on average, every user has written between 400 and 500 posts, and the average number of sentences per user is between 1.2 and 1.7 thousand sentences. So as I've already said, our proposal involves building 21 symptom classifiers that follow the same classification framework based on semantic similarity. In particular, we want to retrieve pieces of evidence for depression using semantic search on the user posts. And in order to do this, we need to select candidate posts, that is, and candidate sentences representing the user, and compute depression scores between these representative sentences and sentences representing each option of each depression symptom based on semantic similarity. And our classification framework relies on 2 components: silver sentence selection and semantic retrieval pipeline. The training labels for each symptom are initially available at user level because each user has filled out a questionnaire where we have all the scores for each symptom, and they are symptom responses. So for example, here the user selected response number 3, I feel I'm a total failure as a person, for the symptom past failure. And then on the other hand, we have all the writing history of this user. So this is the material, how we build our data. We select candidate sentences related to the symptoms, and then to obtain those silver sentences, we experiment with 2 semantic similarity methods: the lexical retrieval baseline based on the BM25 model, and the semantic retrieval, which is based on the SBIRD model. And we use the option chosen by the user as the query, and their writing history as the corpus to retrieve and create the silver labeled sentences for each option. And as I said, semantic similarity is at the core of this relevance computation. To select all silver sentences for an option, we process the same query with all users that have chosen that option. And the selected silver sentences have that option, have the associated label of the relevance and of the option. So like this, so these sentences are relevant to option number 3. And we create an index of silver sentences per each possible option as examples of how people with different responses express each of the 4 symptoms. For example, we denote an index of option I and the symptom past failure as AG of failure, option number 1, and then we do it for each option, building a data set of silver sentences representing each option. Once we have the representative sentences for each option, we perform semantic retrieval based on them. And to do so, we design a semantic retrieval pipeline to predict the response of the user to each symptom. First, we select the sentences from the test user that are relevant to the specific symptom, like sense of failure. And we employ the same candidate selection searching in the test user posts, and we select its relevant sentences denoted as test queries. So here we have a set of queries from 1 to 5, for example. And we call them test queries. The semantic search uses the test queries to produce a rank of silver sentences, and to calculate that ranking, we apply semantic retrieval over the index of silver sentences of the specific symptom, and each silver sentence retrieved in the rank has a label associated. Finally, each test query has a different rank associated, and based on the results of all the rankings, we implement different aggregation methods to obtain a different score for each option. An option with a higher score will be the one that is predicted to the user and that symptom. So here, for example, we have for the user this representative set of different query sentences. We compute the rankings and then we aggregate them. And for each of the 4 options, we have a similarity score. So here we have the scores 0.8, 5, 3, and 1. And the option with the most high similarity, which is the first option, I do not feel like a failure, will be assigned to this user. For the evaluation of our method, we follow the metrics that are proposed by the e-risk organizers. There are 4 different metrics, 2 of them on the symptom level and 2 of them are on the questionnaire label. And we use as the baselines the best prior work for each metric considered. And these are the final results. So we test on 2 collections, 2020 and 2021. And then you see the set of baselines that participated in that task. And our own methods, where we use different aggregation methods and also different retrieval, semantic or lexical retrieval methods. And then we can see that our approaches are better on questionnaire metrics. So it is better in estimating the overall levels of depression in the user. However, we underperform a bit the metrics associated with the individual symptoms. And in general, both for baselines and for our method, whose big advantage is that we don't need a manually labeled data set. So we still have a large room for improvement in this task. So in summary, I'd like to highlight that our framework is competitive with state-of-the-art approaches who used manually labeled data to train the classifiers, different to our weekly supervised approach. And we reformulated the depression detection task to classify between different severity labels and rely on symptom-based predictions with several benefits in terms of interpretability, because we don't only have the overall depression severity score, but we also have symptom level scores that we can examine. And the adaptability of our method allows us to aggregate our features to other depression specific measures and extend our method to other similar diseases and measurements. We would like to note that we have a distribution bias in our data. The classes are not equally well distributed, and in future work, this is something that we are considering to de-bias. And also the weak labels contain many false positives that introduce noise, which is why we think that our current results can be significantly improved in future. The limitations of this study include the following ones. The performance is still insufficient to be integrated directly in clinical settings. And also our pipeline currently lacks external validity. So we have started a collaboration with the clinical psychologists to test it in a real clinical setting. And the data set that we use has a limited size, which highlights the general problem of applying AI and NLP techniques in the mental health setting. The data is extremely rare, small, and also hardly accessible without a complicated negotiation process. And we think that certain errors in symptom estimations based on our error analysis may be due to a lack of awareness of the individual, of their own condition. This is something I talked about in our first project, that affected individuals are not always able to accurately describe their emotions using the words, but also maybe due to stigmas associated with the different symptoms, where the users may not select the true symptom based on the stigma they associate with it. And in conclusion, we presented a simple yet effective and scalable pipeline to estimate the depression levels of individuals from social media. And our approach is based on decisions in the presence of clinically validated symptoms collected in the BDI-2 questionnaire. We proposed different data selection strategies to select candidate sentences and build a training data set in a semi-supervised manner. And we achieved competitive results which are comparable to supervised approaches employed by the state-of-the-art on this task. So the summary of the talk is that I've presented the importance of AI and NLP in the domain of mental health, and in particular applied to affective disorders such as anxiety and depression. And I've shown two projects, the first on predicting client emotions and associating them with the emotional coherence and the client's well-being, and the second on estimating depression severity in social media. And during this experimentation, we have learned many lessons. Of course, we all know that collaborating with other non-technical disciplines is extremely challenging and time-consuming. And also, before we can start working on interesting NLP questions, we first need to figure out the way how we can apply existing techniques, and only then we can start the experimentation with new methods, which is always quite a long way. And one of the obstacles, which in my experience reoccurs in such projects, are very strong privacy concerns. And also in publication, we cannot make the data public and available to other researchers, which requires experimenting and designing novel privacy-aware approaches that we are also considering now in our ongoing work. So nevertheless, I'm very convinced that technology can help a lot in this area, which is extremely important to the society. As I said, the numbers in mental health issues are really pandemic. And with the technology, we can improve the treatment and we can personalize it to target a specific patient and their trouble and be able to treat it effectively. Thank you very much for your attention, and I'm looking forward to the discussion.
Thank you.
Hello.
Hello.
Okay, you can hear me. I thought the connection was lost again.
No, it's there, yeah. Thank you, Professor Iryna, for such an interesting and enlightening talk. So I will now request the virtual audience to please type in their questions in the Q&A box, and I will ask the physical audience if they have any questions. Yes. Anyone? Yeah.
So you talked about the severity of the depression, where like it's not like a binary classification where it can be severe or not. You are grading it in terms of different scores. So I was just wondering, what is your experience when you say that you people collected data from social media? So for same symptoms, do you think like it makes sense to train different classifiers for different social media platforms? Maybe people express differently in different kind of social media, for example, Twitter, Reddit. So like there are text limits, and also obviously the people's nature changes, behavior changes in other cases we have seen for like different kind of social media platforms. So do you think like it would be more useful if you can think of like separate classifier or separate models for separate social media platforms? So that was just a general question.
Yeah, thanks a lot for the question. So as I said, collecting data for this is extremely challenging due to ethical reasons. I mean, with the social media, we also have these license issues and all this, but for mental health, it's even much more challenging. And in our project that I presented here, we used already existing test collection from CLEF. So your question is if we need different models for different types of social media. So, I mean, I can just speculate because we have not carried out any such experiment. But I think that this may be well the case. So first of all, the population of users in different social media may be different, and they may use different, for example, more formal or more informal language, depending on the media. And also we know that the language varies a lot. You know, in Twitter, we have very short messages. In Reddit, we have longer posts where people talk about their issues. So I do think that that will be a big challenge to model generalization, right? But this is just my speculation because I'm not aware of any empirical evidence to answer this question properly.
We have some questions from the virtual audience. Shall I read out the question from Iryna? Typically, in such an interdisciplinary project, due to the requirement of interpretability, we would use something that's relatively simple in terms of methodology. Then feel there's then limited room to make contribution in terms of NLP. How do you view this?
Yeah, I can absolutely share this opinion. I actually commented on that. So, for example, in the depression severity project, our methodology has the advantage, though we don't have really advantage in terms of final numbers, but compared to baselines that use deep learning, so we can show the score for each symptom instead of just classifying everything. And we can also highlight the sentences that led to this classification because we know the most similar sentences. And right now in our collaboration with the clinical psychologist, he's looking into this data. So our approach has the advantage of having higher interpretability. However, I would not say that our approach is particularly simple. I think semantic similarity is a very general notion, and I think we can target it much better to this task in future work than what we have done so far. We just took the off-the-shelf existing classifiers. But I do think that getting to the stage where we can do interesting NLP research is much longer, because we first need to gain an understanding of the task and also find a common language with clinical psychologists. That is, we need to learn their discipline and they need to learn ours. And typically that takes a lot of time, and this is not particularly rewarded in the NLP community, because one might get comments from the reviewers that while this is all interesting, but there's no novelty in NLP. However, to get there, we need to first go through a complicated process of formalizing specific clinical task and applying simple techniques in order to understand where we stand and where the room of improvement or, the challenges are in general. But I think this is the cost we kind of pay for interdisciplinary research. And the only way to deal with this, we need to increase the awareness in the NLP and AI community of the importance of such experimentation. And, we need to adjust our reviewing values to recognize this.
Thank you. We have another question. Could you elaborate more on the practical application of predicting emotional coherence? Because in the model, there are 4 labels in total for the emotions, while we know that we have many more emotions. How do you think about this?
Basically, in this case, I mostly rely on our collaborators in clinical psychology, and they said it's better to start with something which is simpler and understand this on this level first. So we have 4 labels: positive, negative, mixed, and neutral. And in future work, one can have a more elaborated theory that we have here, but then it needs also to be connected to the theories which are used in clinical psychology. So what they use right now is pretty coarse-grained. So I think personally that more fine-grained models could bring additional clinical value, but that will have to be validated empirically, because basically in the first step, they will need to create a data set which is more fine-grained, and then they will need to seek, more detailed analysis if this is how this is correlated with self-assessment of clients, of their emotional state and well-being. Maybe it brings additional value, but maybe not. But in our results, we can confirm this effect even for the coarse-grained labels that we have used, because we have found statistically significant correlations that are evident.
Thank you. We have another question from Jonathan. How does this research cater for cultural differences? For example, informal language or slang that many regions use may connote markers for depression, but in itself is just a common expression in that region.
Yeah, that's a very interesting question. We are planning to do a cross-language study, approximating cross-cultural study, because we can experiment with data sets collected in a specific country. But this experimentation somehow cannot be really executed yet, because we are still in the process of negotiating the contracts for being able to use the data. I mentioned that the availability of this data is extremely limited, and it's not common in clinical psychology to share the data sets or to give them to other researchers for experimentation. So that requires a contract, typically, in my experience, at least if we really want to use clinical data sets that are collected in real life therapy. So far, we could not run this experiment because we are in the process of negotiated, and it takes a long time. But once one could, so that would provide very interesting insights into different cultures. So it boils down, in my opinion, to being able to gain access to such a cross-cultural data set, either from a clinical setting or from the web. But again, on the web, we also have the difficulty how to associate the users with cultures. And given the low number of users we have at all, the possibility for studying this are limited. So the data is 90% of the business here, in my opinion.
Yes, yes. Thank you. We'll just take one more question, Professor Iryna. The question is, I wonder if you could expand more on the challenges experienced from working with clinicians and psychotherapists and what you have learned from it. Any recommendations for other NLP researchers aiming to have a fruitful collaborations with clinicians?
So I have a lot of interdisciplinary collaboration before I entered this new topic. I actually started working on this only 2 years ago, so it's a new topic for me, but it's similar. In my previous experience, I collaborated with educational researchers and with people from the humanities. It's quite similar. So I think it takes additional time to learn the basics of their discipline, because we only can productively talk to each other if they understand a bit what we are doing and and we understand a bit what they are doing. And it's just like 1 year doing some master level courses and doing a lot of reading, basically just to get to this level, and that consumes time, right? So that's kind of a challenge. On the other hand, regarding this topic, mental health, psychology in general, I really enjoy the topic. So I have learned.
I think we lost a connection. Yes.
So I'm back again. So
Yes.
I just wanted to mention that our collaborators also had prior experience in collaborating with NLP and AI people. So it went much faster for this reason. So we could identify common ground much faster. And regarding the publications, I have to say we were not able to publish much so far because it took long time. But I think now we have built the foundation, and I think now there's a lot of, I have not mentioned this in my talk, but maybe I should raise it, really a lot of ground for experimentation with generative NLP. So it's amazing how good the large models are at simulating the psychotherapist or at simulating the patient. So we have like millions of ideas what can be done with it. So after some time, the effort is becoming less. But I agree, for PhD students, it's quite challenging. So I think that you should choose this topic if you're really fascinated by, by this whole domain. Then I think, maybe you need to invest a bit more time, but this investment has potentially very, very huge impact. And this is why I'm doing this and how I can convince my students to work on this. Because, in other areas which are more technical, you can publish some small improvement and maybe you can have a quicker publication. But what is the impact of that work, in the long run? I think the impact may be very little despite having this publication. But in the areas of social good in general, and this area I was talking about in particular, so there's really so huge demand. So people, wait in Germany for half a year before they get a first slot to talk to a psychotherapist. And they suffer so much. And I mean, some people can even commit suicide. So we can really have a lot of impact in real world and a lot of visibility, by the way, if we manage to propose solutions that help many people. And this is why I think it's worth, putting the impact maybe not only on short-term publication in some venue, but impact in terms of how can we change the world to the positive. And of course, we have enough venues which are interdisciplinary. where we can publish. So I think so publications can be done to fulfill a PhD requirement, plus potentially one can have a lot of impact and visibility and also helping people. And that's why I convince my students to work on this. And this area has been very much growing in the recent time.
Yes, yes. Professor Iryna, you mentioned about the data set that you created. While we understand the clinical data you can't release for researchers to use, that's the Hebrew language, but the social media data that you annotated for the 21 symptoms, will that be made publicly available for researchers?
So that data is freely available from CLEF. So we have not annotated anything. We use their data set. So you just
We lost her.
Yeah, I'm sorry, but at least I can come back very quickly.
Yes.
So just repeat the answer. For the social media data set, the data is from CLEF.
Okay.
You send a license with them and you get the data sets without any problem. So it's directly available. For the body-lung clinic, the data may not leave the clinic. So that's always very often the requirement of the user consent, that the data stays in the clinic, right? And we have different, we cannot publish the data, of course, it's clear. And by the way, this is the reason why this paper has been rejected 2 times.
Yes.
You know, though we try to give all arguments why we cannot release the data, but some reviewers are very agnostic, you know, of this. So they just require to release the data, but it's not possible. But we want to do this research independent. You know, we want to make progress with the issues helping mental issues. Anyhow, I think there is a lot of development in differential privacy. And in short term, in 1 year, there will be approaches how we can give access to such data for external people without really releasing the data. So we can rephrase the data and make it safe, or we can create a data enclave, right? So I think the problem will be solved.
Hopefully. Yes. We have one question from the physical audience. Yeah. Just a second.
Hi, Iryna, Fabio Zanzotto from Italy. You know me.
Hi.
Hi. I just want to drop you an email about either your fields.
She said.
I'm sorry, but I cannot really understand you well.
Okay, I'll try again. I will drop you an email because I'm working on this privacy issue on a project, and possibly I have a kind of solution. So if you are interested in, I will give you access to this paper, which is called Active Informed Consent, and I'm working on that.
Okay, that's great. So thanks for the comment. And I would be really grateful if you shot me a message after the talk, because I could not catch your name, unfortunately.
Sure, I'll ask him to drop in an email.
Thank you.
Yeah. Thank you, Professor Iryna, for your time and support for this event. It was wonderful listening to your talk and your contributions to the field of penalty for social good. Thank you again for joining us.
Yeah, thank you so much for this very patient audience. And sorry for interruptions. And I wish you a very great second day of the symposium. See you soon at conferences. Bye-bye.
Thank you. We'll take a break, right? Yeah. So we'll take a 15 minutes. We'll take a 15 minutes break and we'll join after that for the next talk.
Okay. Okay, thanks, Projata, for the introduction, and thanks for having me here. I'm really glad to here to discuss with you on this topic, probing and infusing biomedical knowledge for pre-trained language models. It's basically a connection between the knowledge graph and pre-trained language models, and involving two tasks: the knowledge probing and infusing. So let's see what is knowledge graph. So knowledge graph. Yeah. The dialogue. Oh, okay. Thanks. So knowledge graph are basically a set of facts represented as triples. So where each triple represented by a head entity, a relation, and a tail entity. And so here I show a small knowledge graph of Mona Lisa. And here, one of the triple here is a Da Vinci paint Mona Lisa. So here Da Vinci is a head entity, and paint is the relation, and the Mona Lisa is the head, is the tail entity. So this entity can be obtained by many different sources, such as Wikipedia-based knowledge, such as Wikidata, Wikipedia, and Wiktionary. They can, we also have some general knowledge bases, which is structured, such as Freebase, DPpedia, and Yago. And in some domain-specific knowledges, we also have some domain-specific knowledge graph, such as in the biomedical domain, we have MeSH, SNOMED CT, and UMS. UMS is one of the largest thesauruses that contain 150 different ontologies, which including also the MeSH knowledge graph and the SNOMED CT. Here you can also see in the biomedical domain, the knowledge graph can even be more complicated because we may not only contain the textual entity, but also some biomedical entities such as gene and compound. So compound, we know it can be a certain drugs. So this is the small molecules. And gene is actually a sequence, right? It can map into a particular proteins, which is organized by amino acids and a disease. So gene can associate some kind of disease, and compound, which is drug. The drug can treat certain disease, and disease can be associated with certain symptoms. So symptoms we normally utilize as present as the textual data, right? So this knowledge graph can be obtained by many different ways. Traditionally, they are obtained manually by humans. So people may do some research, they observe the world, and they got some conclusions, and they publish as an article in some journals. And then some people also try to read the papers and extract some factual knowledges. And then they organize them as the knowledge triples, which is the head entity, relation, and tail entities, then store in the knowledge base. With the current technologies, we can also use some NLP techniques to automatically extract these knowledge. So given similarly input text, which can be some scientific articles, and we can use various NLP techniques such as name entity recognition, categorization, relation extraction, and entity linking. We extract some entities from articles and extract the relations and organize into triples and store in the knowledge graph. They are quite the pre-trained language model pre-trained process is actually quite similar to the knowledge graph construction process. Let's see how it is. For the pre-trained language models, we are normally taking a large corpus as input and initialize some like transformer parameters. And then if we join the training with some pre-trained objectives, and we obtain our pre-trained language models, right? And for knowledge graph, we similarly will take some textual data as input, and then we utilize some tools such as name entity recognition, relation extraction, And then sometimes we also use the pre-trained language models as the backbone or as kind of tools to do these tasks. And then we obtain our knowledge graph. So actually, as we know, for pre-trained language model, we try to gather as many corpus as possible. So sometimes these textual data utilized to construct knowledge graph has already included in the pre-trained corpus, right? So they may identical to each other. So in that sense, why not directly use pre-trained language model to predict knowledge triples? Because this textual data has already used for pre-train a language model. So this is some motivation of why we need to connect a language model with knowledge graph. Let's recall how we do the pre-training for BERT model. So BERT model, as we know, they are pre-trained based on Wikipedia and Google Corpus data, and by a bidirectional transformers. From this training corpus, we may randomly sample one sentence from the corpus, and we randomly mask some of the tokens, right? So in this sentence, we may contain some entities because the world is organized by factual knowledge. So knowledge may involve some entities and their relations. So here you can see that we have actually 3 entities here. Inception is a science functional verb. So we have this is one kind of knowledge triple, and inception is directed by Christopher Nolan. So this can be another factual knowledge. Then we mask some random tokens in the sentence from the sentence, and sometimes we just exactly mask the particular tokens, and we ask pre-training model to recover what is the mask tokens. Ideally, the pre-trained language model can recover such mask tokens. For example, in this case, it may ideally can predict the missing token is actually Christopher Nolan. So in that sense, we actually can predict a triples, right? Given the tail head entities, given the relations, we can predict tail entities. So in that sense, because we have many thousands, hundreds of these sentences, and we feed them in the pre-trained language model to pre-train over many times. So this pre-train process is actually a knowledge acquisition process. We can even do that reversely. Given a knowledge triples, we can formulate as a sentence, and we mask the tail entities. And we ask pre-trained model to predict what is the missing token. Ideally, the pre-trained language model can predict the exact mask token, which is the tail entity, right? We can test that with some examples. Actually, some research has already done that. And they randomly sample some knowledge triples from the existing knowledge graph, and they formulate these knowledge triples into sentence, and they marks one of the tokens, and ask a pre-trained model to predict what is the missing token. So we can see that the pre-trained language model actually did pretty well in predicting these missing tokens. And for example, iPod Touch is produced by Apple, and London Jazz Festival is located in London. This is easy for a language model to recall such knowledge. Even we didn't explicitly feed the knowledge triples into the pre-trained language model. So potentially, so this suggests that potentially we can regard a pre-trained language model as knowledge base. However, we have many different models. We have different models, different pre-trained models are pre-trained over different corpus. For example, BERT was pre-trained by based on the Wikipedia data and Google corpus data, right? And some biomedical domain specific pre-trained language models, they are made pre-trained based on different corpus, like the SciBERT was pre-trained by PMC and SCS corpus, and PubMedBERT was pre-trained based on PubMed articles. So they perform quite different over different applications. So what is the best language models to serve as the knowledge base? So this is some question we need to answer. And how could we measure how much knowledge has been stored in the pre-trained language models, right? And given that we have many different domain-specific applications, how do different pre-trained language models differ in capture different domain-specific knowledge? So this actually calls a new task called knowledge probing. So which is try to measure how much knowledge or domain-specific knowledge has been stored in the pre-trained language models. So for the knowledge pre-training task, knowledge probing task, we actually care about a pre-trained language model and a knowledge graph. We don't care about how the knowledge graph is constructed. We assume that knowledge graph is some factual knowledge has been curated humanly or automated extracted. At this, it is less noise compared to the pre-trained corpus, right? So we taking this knowledge graph as kind of benchmarking data sets, and we ask pre-trained language model to predict what is the missing factual knowledge. So this is the basic definition of knowledge protein task. So to achieve this goal, we basically need to do two steps. We need a benchmarking data size. So these data sets can be corrected from some knowledge graphs, as we mentioned, right? It can be like wiki data or some other biomedical specific knowledge. And we need a probing approach. So given the benchmarking data sets, we measure how much knowledge has been stored in the pre-trained language models. Lemma is one of the most popular work has been doing in the general domain. They basically build a benchmarking called Lemma, which is corrected from 4 corpus, such as Google RE, T-Rex, and ConceptNet, and Squared, and organized by different types of relations. And they also propose approach, as we mentioned, is basically try to formalize the input triples as a sentence, and then mask the tail entity, to ask a pre-trained language model to recover what is the missing token. And we call this approach as mask predict. One limitation of this approach is because this work only conducted in the based on the BERT models, the encoder-based pre-trained language models. So they require that the knowledge triples, the entities in the knowledge triples should be single token, because we know that the pre-trained BERT has a masked language modeling head, which is the pre-training objective. So given the sentence, if we want to recover what is the mask token, we require that the mask token should be in the vocabulary of the pre-trained language models. So for these benchmarks, actually all the entities are already in the vocabulary of pre-trained language models. So which means all the entities should be single token. However, we show that this limitation, we are not making the probing of biomedical domain super challenging. With this benchmark and probing approach, and some researchers in 2019 have conducted a comprehensive evaluation over different pre-trained language models and some knowledge base, including some naive entity-linking approach. And it turns out that some pre-trained language models, such as DARSH, actually perform much better than the knowledge base, which suggests that actual pre-trained language model can serve as knowledge base because it actually performs better than the knowledge base, right? However, this work was generally conducted in the general domain. There are many biomedical pre-trained language models, such as PubMedBirds, BioBirds, and SignBirds. They have been powered many biomedical applications, such as biomedical question answering, medical dialogue, medical NER. And there's not too much work to do the probing task in the biomedical domain. So following the same protocol, we propose a new benchmarking for the biomedical domain called MediLemma, which is a knowledge graph benchmarking extracted from the UMS, which is the largest biomedical knowledge graph, contains 3.6 million entities. And we also identify many challenges for probing the MediLemma benchmark because they are not mostly single token and their naming systems are heterogeneous. So to address these challenges, we propose a new probing approach called the contrastive. Let me introduce you in this detail. First of all, in MediLemma, there are only 2.6% of the token are single token, versus in Lemma, there are 100% are single token, which making the probing task more challenging. As we can see, that actually most of the entities in biomedical domain actually contains more than 3 tokens. And the second challenge is a significant amount of entities are unnatural languages. It not only contains the natural text, but also some abbreviations, such as like EKG. I don't know what is EKG, but just using those 3 tokens, right? And even if we use Persian language model to tokenize these, maybe just 3 single verbs, right? And also contains some molecular formulas and some diagnostic codes. So, for example, J45.909. So this is a kind of unspecific ASHMA. But if we only input these tokens into the Persian language model, it may tokenize to some random numbers, these collectors, which is not desirable for some Persian language models. There are also many existing probing approach, such as the mask predict that we mentioned before. So this approach can actually extend to multi-token scenarios by using certain refinement approach to given a fixed windows, we can predict some mask tokens. By some refinement, we can obtain multi-token entities. However, it doesn't perform good in the Med-Lemma benchmarks. We can also utilize the generative model like T5 or BART model to generate multiple tokens autoregressively. However, this probing approach only available for the decoder only or encoder decoder only models. And we also see that with this data set, with these biomedical benchmarkings, they perform pretty low in the probing task. And another approach called the mask average is try to use the average embeddings of the mask token. We have many different tokens in the entities and then take the average of all the tokens and use a retrieval-based approach. And we see that all of this approach, if we use this approach to probe under our Med-Lemma benchmarks, they can get pretty low performance because for example, all of them only achieve less than 1 accuracy of Med-Lemma because these challenges in the Med-Lemma benchmarks, which means this probing approach, actually not quite good indicators to compare different models. Recall that the probing task is actually an approach to measure how much knowledge has been stored in the Persian language models. If these numbers are not quite distinguishable, so it's not quite good to measure which is a good Persian language models, right? So to address these issues, we propose a new approach, probing approach called contrastive probe, which is basically a closed-tail self-retrieval game. So this probing approach contains 2 steps, a self-supervised contrastive rewiring and a retrieval-based probe. For the first step, recall that for the probing task, we actually require that the model should not fine-tune over any existing data because we don't want to change parameters or we don't want to add additional data to shift, to change any, to expose any additional information. So here, the rewiring process is actually, we randomly sample some sentence from the original pre-training corpus. For example, for BERT, we can randomly sample like 20K sentence from Wikipedia. For PubMed BERT, we can randomly sample some sentence from the PubMed articles. Then we use this article to conduct a self-retrieval game. Specifically, given a sentence, we split them into 2 parts. The first part being a one entity with duration, the second part being the tail entities. And we ask the Persian language model to predict what is the missing second part. And we use a contrastive loss to ask Persian model to, based on the classification token of the whole sentence, to retrieve what is the missing token. So all the sentence, all the half parts of the sentence will be encoded with a process to get embeddings. and we store in the memory, and we ask the pre-trained language model to retrieve the most closest entities or just half sentence. So after this process, what we do is we slightly shift the original pre-training space into a better knowledge prediction space. It doesn't expose any external knowledge because we only use the existing pre-trained corpus, pre-trained sentence for this process, and it conducts this process can be conducted in a very efficient way. It only takes like 2 or 3 minutes with only a 2080 NVIDIA GPU. So after this process, we can do the retrieval-based probing, which similarly we given a triple, not triples, we mask one of the tail entities, and we formalize as a sentence. We ask pre-trained models to predict what is the missing tail entity. So here we take the classification token of the first part, and we also encode all the entities in the knowledge graph into embeddings, and we use a given the query embeddings, we ask we predict what is the missing entities from the entity embedding, which we pre-encoded by the same model. Here we use the near list neighbor search to get the entities. So here we note that here we actually don't use any prediction height. Instead, for the previous pre-trained language model probing approach, they use kind of mask language modeling height. They use the mask tokens, which you need to reuse the pre-training parameters. But here we don't need any pre-training height or task-based height. We only need to get embeddings of the hidden layer of each transformers. So we can see that with this contrastive probe, we can got much better performance comparing the existing probing approach. Specifically, for the Biomedical bird, we can actually got 24% of the accuracy at 10, and even like roughly 6% of the accuracy. And we can all get much better performance comparing the existing approach. So this number actually is more distinguishable for comparing the ability of capture fractional knowledge. And the contrastive probe also quite robust to the number of tokens. As we mentioned, in biomedical domain, most of token contains multiple tokens. So as the numbers of chairs goes and the entities, we can see that the contrastive probe actually perform quite stable, where the mask predict their performance drop significantly comparing versus the number of chairs. Because we don't need to use the mask language model height, we don't need to use any task height, we can actually measure how much knowledge has been stored in each transformer layer, because we can only extract the representations of the first 3 layers, or first 7 layers, or first 11 layers. Which means if we know that in certain types of operations, this pre-trained language model doesn't perform well, we can intentionally inject this type of knowledge inside a particular layers. We can keep the other layers fixed and only update the parameters of the certain layer, which is quite good. And we actually found this is quite interesting because this figure shows some performance of the lemma benchmarks over the pre-trained language model Biomedical birds. We see that for different layers, they actually have already captured with different performance over different durations. For example, duration 2, this is duration 2. We see that only with the 4, 11 layer or 12 layer of bird models, we can obtain like more than 10% accuracy. However, with over duration 11, we see that with only 3 layers of the representations, we can even get more than 13% accuracy, which is quite interesting because which means we only need to use the first 3 layers. We can still predict quite good entities for these certain operations. And for the last version, which is version 18, it cannot perform quite good in all the layers, which means we probably need to inject this knowledge in all the layers. So this is the knowledge probing task. But here we need to argue that pre-trained language model is not enough, because language model are actually pre-trained based on some random sentence from the word. Some facts may have not occurred in the training corpus, right? Some, especially with the ChatGPT, they are pre-trained based on like 2021, right? Some later facts may not have been encoded in pre-trained language models. And there are also some rare facts, which are not, they have not quite high probability to exist in the world, but they are actually very important, particularly in the biomedical domain. So some new facts maybe not quite frequently appear in the old corpus. So the pre-trained language model hadn't seen enough examples with the same format during the pre-training to memorize such facts. And the third challenge is the model sensitivity. Pre-trained language models may see the facts during training, but it's sensible to the phrasing of the prediction. It's related to prompting technique. So which means in the pre-training stage, we pre-train with a certain paraphrase. But for the prediction, if we change the paraphrase, we may not be able to recall the knowledge, right? And the recent work has found that language models actually can recover some knowledge, but only when they design proper prompts. So here we argue that the knowledge graph may help to alleviate these issues, because with knowledge graph, we not only have the sentence information about entities, but the relations between the different entities, right? Because for the pre-trained corpus, we may use the next sentence predictions, right? We can capture a relation between two consecutive entities. However, for the factual knowledge, we actually need to conduct multi-hop reasoning to get some inferred knowledge facts. So the knowledge graph, which is organized by the relation of different entities, may help to enhance the current pre-trained language model to capture some multi-hop knowledge. And this is the task we call the knowledge infusing. So basically, the knowledge infusing task is to inject some factual knowledge into the pre-trained language models by using a knowledge graph, by using some factual knowledge triples. And the input is a pre-trained language model, such as BERT, and a knowledge graph, such as Wikidata. And the output is a similar pre-trained language model, but with the knowledge encapsulated. So in general, this process is between the pre-training process and fine-tuning process. We have already pre-trained language models by some large corpus, and then we try to inject some up-to-date knowledge into the pre-trained language model, and then use that to fine-tune on some downstream task. There are many exciting work to do these tasks in the general domain, such as EARNING, which is pioneer work to do the knowledge infusing. This model actually utilized knowledge graph embeddings from Wikidata. So it used technique to link the English Wikipedia text to the entity in the knowledge graph, which is Wikidata. So, and they pre-train some knowledge graph embeddings of different, they obtain embeddings of entities by pre-train a knowledge graph. And then they add these entity embeddings of knowledge graph into the attention of the transformers. So this is actually a pre-training process from scratch. Instead of training with master language modeling head and next sentence predictions, they further introduce additional loss function to pre-train to predict the missing entities. And they also modified attention layers to better add the entity embeddings from the knowledge graph embeddings. Papered is another model that utilizes the idea of data augmentation. So given a knowledge graph and a pre-trained language model, so they try to augment the pre-trained sentence into a sentence tree, which for each entity in the sentence, they will link to a particular triples from the knowledge graph. And then they use a they call it visible matrix to control the visibility of different entities among all the entities in the input sentence. It's basically an approach. I think it's equivalent to the same process. Like if we have a pre-trained corpus, and for each sentence we can augment additional sentence to add more connections for those knowledge graph. So this is the caper model. And another model called Kepler, so which they use the idea of joint training with knowledge embeddings and mask language models. They have two laws. The knowledge embedding, they try to, given the head entities and rationally try to predict the tail entity. And the technique here is they use the same encoders to encode entities from knowledge graph and entities in the pre-trained sentence. So in the general domain, there are many more work has been doing this knowledge infusing work. Like here we only introduced 3 earning caper and caper. However, in the biomedical domain, there's not too much work has been done since the year we be doing this topic. So actually we propose 2 work. We have done 2 works here. The first is separate, which we try to infuse the synonym relations from the biomedical knowledge graph into the pre-trained language model by we call self-alignment pre-training. And the second work is called the mix of partitions. We try to inject some general relations into the pre-trained language models by adapter modules. So the first work is generally to try to inject the biomedical synonym relations. The second work is try to inject some general relations. Let's look at them in more detail. So why should we inject synonym relations? As we know that in biomedical domain, there are many different entities and they are organized by different peoples or even in social medias. So there are many entities. They have more than one surface zones in a domain. For example, here, the entity hydroxychloroquine, which is one drug, which Donald Trump claimed which can be cured COVID-19, right? And it actually have an alternative name, oxygen chloroquine, right? Which is another name of the same thing. And in social media, people always use HCQ to represent the same thing. And some people also would like to use the chloroquine here, which is a drug brand for this kind of drug. So they actually refer to the same concept if we talk about these different surface form in the sentence. But if we map them into the pre-trained language model, particularly some biomedical pre-trained language models such as PubMed-BERT, and they actually scattered into different positions in the embedding space, which means they refer to the different things, which is not desirable for some applications, right? So we propose separate, try to inject such synonym knowledge into the pre-trained language models. We use UMS as our knowledge source. UMS, as we mentioned, which is the largest interlingual of biomedical ontologies. This is very large knowledge graph, contains more than 115 controlled vocabularies, including SNOMED, CT, and MESH. It contains 4 million concepts and 10 million synonyms. And then we utilize the 10 million synonyms to be our training examples. Specifically, we organize them as 2 positive entities and the entity ID. And this is our training knowledge graph. And we use 2 techniques to do the pre-training or fine-tuning, which we call self-alignment pre-training. The first technique is smart-only sampling. So we only build examples that they are hard to be distinguished. So in general, if the 2 entities already if we randomly sample some positive entities, if the negative entity already being quite far away from space, it's not useful for the pre-training. So here we try to obtain some hard examples. We try to find some examples where the positive example is quite close to the negative example, right? So after this negative hard example mining, we found the embedding space of the positive example and negative example are much closer to each other. So we are making the task much harder. Making the task harder, which means we can better train the model and the model could be more robust and stronger. The second technique is we use a multi-similarity loss. This is one of the constitutive loss. And the multi-similarity loss is a loss function that we can better control the weight of positive example and negative example. We actually have tested almost all the constitutive loss, and we found this is actually the best one. So after this pre-training process with the UMS synonyms examples, we found that in some entity linking tasks, which is quite useful in the biomedical domain. So we try to find, given the input text, we try to find the entity to map the entity in the text into the entity in the large graph, right? So in the unsupervised scenarios, we found with the separate pre-training, we can significantly improve the entity linking performance. In some data sets, such as ASCII patients, we can even improve the performance by more than 40%. Even in the supervised scenarios, without any supervision signals, we can perform even obtain on par performance compared to the state of art, supervised state of art. And if we also for the supervised state of art, if we utilize the same separate pre-training, we can even boost the performance by significantly. So this is the work we focus on injecting the synonym knowledge. And the second work is we try to inject some general relations from UMS. So UMS is the largest biomedical knowledge graph, right? So, but there are still challenges when we try to inject them into the pre-trained language models. The first challenge is these entity sets are very large, because here we only focus on the bird model, and we try to inject the biomedical knowledge into the bird model. So we can utilize the mask language model height, but we see that, as we mentioned in the probing task, because most entity have multi tokens, so we cannot directly use the mask language height to inject the knowledge. So we may think we may need to directly use a prediction height, which is directly to predict entities. Given the head entity and the relation, we try to predict what is the missing tail entity. So this is basically a classification task. We try to classify an entity into, for example, if we're using a UMS as our training corpus, so we need to classify into 4 million different entities. So the soft marks will be exhausted. So it's impossible to do the soft marks for the prediction height. We can actually reuse some like mask predict by predicting multiple mask tokens and with the refinement, but empirically predicting multiple token using bird is not effective. And another challenge is the heterogeneous naming system. As we mentioned, in biomedical domain, there are many abbreviations, molecular formulas, and diagnosis codes. So which also challenging for injecting knowledge. So here we propose an approach called mixture of partitions. So because the knowledge graph is super large, so we try the divide and conclude strategy. We try to divide the large knowledge graph into smaller subgraphs. And we use adapter modules to inject the subgraph-based knowledge into the adapter modules. And then after repeating this process, we can obtain separate adapter models with the knowledge encapsulated. And then we use a mixture layer to mix all the knowledge from different subgraph to do the downstream task. That's the basic idea. So here we use adapter model. I think most of you have already know that this is one kind of parameter efficient tuning approach. So we only need to add additional newly initialized parameter inside transformer layers. And during the training process, we keep the original pre-trained parameters fixed and only update the parameters of the adapter module. So this is diagram showing the idea. So for the BERT model, we only use encoders. We only need to inject some parameters here. And during pre-training, we keep all the parameters fixed and only update the right model. For partition the graph, we have three requirements here. Because in UMS, we actually have 10 millions of knowledge triples. So we try to maximize the number of resulting knowledge triples to retain as much factual knowledge as possible. Because if we try to split the graph into small subgraphs, we will need to remove some triples. However, we try to reduce the removed triples. So this actually can be reduced the task of a minimal cut. Unfortunately, this is actually a very classical computer science problem, which is a bit hard problem. So we cannot find exact solution for the problem. And the second requirement is we need to balance the nodes over different partitions to reduce the overload parameters across different entity prediction heads. Because we focus on the BERT models, right? And we try to utilize the entity prediction task, which means we need to do a classification. We try to classify into the entities with a vocabulary of over the subgraph, right? So which means we hope that all the subgraphs should have equal number of entities, so that for each sub-adapter modules, we have equally same parameter size. The third requirement, we need efficient at scale because we have, as we mentioned, we have 10 millions of triples. We need to do that pretty fast. Mattis is only one algorithm we found that could meet all the requirements. It basically uses a cosine and a partition, a cosine and cosine idea to obtain any number of subgraph in like just 3 minutes over a billion size knowledge graph. And after we partitioning this large knowledge graph into smaller subgraphs, we use adapter to inject subgraph factual knowledge into the adapter modules. So here we use a entity prediction head. I basically utilize the head name, head entity name, and the relations, and we ask pre-trained language model to predict what is the missing tail entity. And in general, this entity prediction objective it contains a softmax head over the subgraph entities, which is roughly a set of 17K or 30K. For the mixture layers, we have many options. For example, we can use original adaptive fusion, which will be they use a softmax style fusion component to fuse the knowledge for different adapters. We can also use combo softmax, which try to make the contributes of different adapters more discrete. And the third one is we also try the sparse gated mix of experts, which we only focus on the top K discrete expert from the older adapters. But empirically, we found the adaptive fusion original softmax performed the best. And we evaluate this model in many biomedical tasks, including the document classification, question answering, and some natural language inference tasks. And we achieve sold-out performance on 5 of the 6 biomedical tasks, particularly in the medical QA task, which is a multi-choice question answering task. But this task we only evaluate in the US medical licensing examination task. This is a full option multi-choice a question answering task, we can achieve like 38% of the accuracy, which is not too bad, but it's not yet past the examination, which requires 60% of the accuracy. However, we will see later, as we are in the time of large language models, such as ChatGPT or GPT-4. Now, this task has achieved like 81% of accuracy, which achieved the expert level. So now we are in the time of the large language models. Since like 2020, the purpose of GPT-3, most of companies or institutions are focused on very large language models, and they try to gather as many corpus as possible to inject all the knowledge inside. And then now we have like GPT, we have in Google, we have a Palm, and GPT-4 just released a few months ago, right? And some research also show that actually the large language models has the ability of encoding clinical knowledge. So that they judge about this plan by evaluate the large pre-trained language model over many biomedical tasks, especially the medical question answering benchmarkings, including some questions like Biomedical QA or MedQA that we evaluate in the mix of partition work. And they utilize the idea of prompt tuning and the instruction tuning. And then now they got obtained performance of 67.6, which means this is the first time the large language model have passed the US medical license examination, which is quite interesting. And not only the classification, they can also provide some explanations. And GPT-4, right? GPT-4 further boosts this task, the MedQA performance to 81%, which achieve an expert level. With only 5 shots of training examples, GPT-4 have obtained like 81% of the accuracy. Even without any training examples, in a 0-shot settings, they can even obtain like 78% of accuracy, which means they can be officially a legal doctor, right? There are also many other biomedical applications has been boosted by the current large language models. For example, some people also use language models to do the drug discovery task, and also the Japanese medical licensing examination task, and also utilize the large language model to encode the gene and the proteins, and also the AI chatbots for the medicine. Right? However, there are also some concerns. I think also mentioned by the previous speakers, there are many privacy issues, right? Because if we use the API of OpenAI, all the query will be submitted to the server of OpenAI, which may bring some privacy issue and some ethical and legal consideration. So if we suggest a treatment for a patient and the patient died, who will be responsible for that, right? And the limited explanation and interpretabilities. Actually, the ChatGPT always like use some fake explanations. They try to justify their argument. Maybe it's not actually factual knowledge. And the unassessed reliability, which means we don't know which language model is better comparing the others in terms of factual knowledge, right? So we can actually, for these concerns, we actually use the probing approach. If we can create a general knowledge benchmarking that is corrected by some knowledge graphs, and we use this benchmarking to probe this large language model to see which perform better, right? And the last one is the lack of domain or up-to-date knowledge. So this is also a common issue that has been researched by many researchers, because the pre-training process of large language model is quite long. Like GPT 3.5, they need like half a year for pre-training and another half a year to do the reinforced learning with human feedback, right? So it's impossible to inject up-to-date knowledge into the language models. So another direction would be we can maybe use some parameter efficient tuning to inject some up-to-date factual knowledge into the pre-trained language models. which is the topic we covered for the knowledge infusing. So let me conclude this talk by some takeaways. The first takeaway is try rewriting process to rewrite the pro-training language model to shift the model into a better task space. So this idea is used for the probing task. We try to use a few examples from the original training corpus to better shift the language model to perform better in a targeted task. So actually, this is quite similar to the idea of instruction tuning and prompt tuning, right? So it's just based on some proper design prompts. We try to make sure that the language model could understand the query, could understand the task questions. So this idea also was inspired by the Mirrorbird, which is one of my colleagues in Cambridge. And the second takeaway is try parameter efficient tuning. This idea was used in the mix of partitions. We utilized the adapter model to inject knowledge into the BERT model, right? And we can also combine prompt tunings with adapters or other parameter efficient tuning. So we have many actually parameter efficient tuning available, like prompt tunings, a bitface or LoRa. So these are also has been deeply researched in the community. The benefit of using the parameter efficient tuning is we can actually modularize the external knowledge, right? Just in the idea of mix of predictions, we can, for each subgraph, we can have a separate adapter module to inject some specific knowledge, and then we can combine them together. And it's also a very good way to adjust the catastrophic forgetting issue. Previously, if we directly fine-tune the model into some specific task, they may forget the previous stored knowledge. And last is try, divide, and rule strategy. So this is also quite hot topics in the current large language modeling research communities. They try to do kind of knowledge distillation or use the mix of experts. So some people, I see in the Twitter, some people think the ChatGPT maybe is a mixture of experts, right? They may have many different models, but they just have some kind of query filtering to decide which query should be a response by a specific expert. So that's all for my talk. Thank you very much for your attention.
So let's take questions. Anyone have questions here? I can see two virtual questions, I suppose. I don't have. Oh, okay. Oh, hold on. The mic is not.
Okay, thank you for the wonderful talk. One of the first things that come to my mind is if you are giving a first part of the talk, which is your research to 2021.
Yes.
And then you say the ChatGPT escape, and basically it went 40 points before advanced 40 points your research. So is there any room for other research for us?
Yeah, I think the loop is if we feed all the testing data in the pre-trained language models, they can perform 100% of accuracy, right? I think it's a high debate topic because we don't know what training corpus was used in the pre-trained language models. And I think we need some other evaluation, maybe more up-to-date training or testing evaluation data sets to evaluate their performance. Because these numbers are actually not so comparable, to be honest.
If they already know all the questions and the answers, if they already seen the test, they are cheating.
Yes, that's true.
Okay, I had one small question. So can you go back to that subgraph screen where you're dividing the whole graph into subgraphs? Will you just comment on the size of the subgraphs compared to the whole graph?
This one?
Yeah, three subgraph model.
Can you just close this one?
Oh,
I think the previous one, when the partitioning the graphs and based on each
This
graph.
one?
Yeah.
okay.
So just comment on the side. If you are partitioning the whole, what is the kind of the size of these graphs in general? Because I'm thinking of it in terms of, like, suppose you want to infuse some knowledge where, like, there is not much data, like very few data.
Yeah.
So, like, how much data you think is generally enough to perform well for a new ontology that we are developing? Or something?
Yeah. So here we only we actually use two training data to the task. One is S4 and the other is like we curated 20 relations. But in general, the training corpus is not so large. I think it's roughly 400K. And we try to, because we noticed that if we try to get a good performance, the soft marks should not too large. And basically a good strategy is we maintain the soft marks being roughly the same number of entities. The same should to the vocabulary of original training corpus. So we have a like 20Ks for each subgraph, and just for the evaluation, we only like try to divide the whole knowledge graph into 20 subgraphs, and we compare the performance of different ones. So here we use randomly some relations, maybe remember correctly, is 120 relations, or we curated 20 relations. And we found that actually 20 relations perform better than the random relation, because I think the 20 relations is more relevant to our target task.
Yeah. Thank you. Thanks for the answer. You don't have any.
Am I loud enough? I see.
No, audience and online.
Yeah, thanks for your talk. I have quite a few questions, but I'll probably ask you too. I think right about the time you probably might have been doing this. Are you aware of Biolama?
Yeah.
You're aware of Biolama?
I think it's a concurrent work because I meet the guy actually. He's from Korea.
Or is it?
Yeah.
And they were more focused on just preparing a benchmark.
Yeah, they only propose a benchmark and they didn't do a probing. So for the probing approach, they only use the existing ones. But so the performance is not quite good. And here we not only propose a new benchmarking, we also propose a probing approach.
Yeah. So regarding the probing approach, what does it look like if you just, use the basic objectives when you're infusing the knowledge, and you just introduce, like for instance, there was one that introduced besides the next sentence prediction and the mark language volume that each I think entity detection and entity linking. It just introduced them at the pre-training stage. Yeah. Right. Well, yours is always gets a bit more sophisticated when you do the contrastive learning. And
yeah.
So how does that? Did you compare with those ones that just literally infuse knowledge using basic pre-training objectives without this contrastive?
I think the question is for the second part for the knowledge infusion.
Yeah.
That's a good point. I think because we're doing this work is we tried directly use the mask language modeling height to inject knowledge, but we didn't notice any performance improvement. And particularly, we see that such as PubMed birds, they are pre-trained based on the PubMed articles. They have already actually utilized many domain-specific textual corpus. So even we use the knowledge graph and we use the mask language modeling height, we didn't observe any improvement.
Rather than doing this for go besides, you compare your work with someone who just introduced like an entity detection objective and an entity linked objective at a pre-training stage, and this from the mark language modeling. How would that compare with this contrast?
But for the second part, we actually didn't use contrastive loss. We only use a soft marks we take that as classification task. We try to classify the mask token into to recover the masked entity. So the entity can be like 20K vocabulary, and we try just like the mask language model we had. We mask a token, but here what we mask is an entity rather than a single token. So I think the constructive loss is we used for the probing.
I understand all of that. My question was simply, how would it compare with just simply because it's like a knowledge enhancement process. Right? You're trying to introduce extra knowledge to a pre-trained language model using an external knowledge base such as a knowledge graph, right? If you introduce just an extra objective, like an instilling objective in the pre-training stage, how would that work? Because there's work that simply do that and they perform quite well. But anyway, we could do that. I'm interested in the heuristics of splitting the two sentences. I think that was at the knowledge probing phase. When you say you split the two sentences, right?
One sentence into two parts.
Yeah. So how do you know where, is it like the supervised splitting?
No, it's unsupervised.
So
it's a supervised actually.
So just so you know that where it gets is black, that the tail is in one sentence and that.
But the objective is actually a random sentence, but we only regard the entities belong the same sentence as the positive, right? For one sentence, we have first part, second part. The second part is the supervision signal for the rewriting process.
Yeah, but one thing, what if you end up with in your like evaluation set where like 50% of the evaluation data points are both the head and tail in one sentence. When you split the two sentences, what if you end up with both the head and tail in just one part of the sentence?
It's a render. We don't care about the actual meaning of the mask, the tokens. So it's just try to let the model be familiar with the task of predicting a entity. So that we don't care, it can be random sentence or just random generated tokens. So the rewriting process is just that the model, pre-trained language model, to better instruct it for the entity prediction task.
Yeah, anyway, I will probably have a chat out.
Yeah, thank you.
Thank you.
So if we don't have any more questions, then we can just end the talk here, and thanks again for so now Danushka will give a brief presentation on the work in our lab. So.
Thanks for making all this time. So, I'll take the last 15 minutes to thank everyone involved and quickly tell something.
The screen is not shared with the.
Oh.
Did they hear me? I beg, if you give me like 10, 15 minutes, I did one symposium, but we did they go do final closing ceremony like in the next 10, 15 minutes. So now we think we'll wait for now.
Yeah, I'm unmuted.
You good now?
Yeah.
Right. So I'll use the last 10-15 minutes to express the gratitude to all the people involved and to tell something a little bit about the social good of NLP, hoping we can continue these efforts in the future. So, not that much long ago, like 10-15 years back, when somebody asked me like what you are doing, and I say NLP, people don't know it, right? So you then have to explain, saying things like that's if you use Google for searching, or if you use within translation systems, then that's the type of technology that powers these things. I didn't understand you. But when people ask what I do in I don't have to tell anything other than just one word now, ChatGPT. And I said, everybody knows that. So we have come a long way from early back office models and creating rule-based systems to the type of technology that we have. So we shouldn't take things for granted. There's a lot of research and efforts going on in the community to come to this level. So that is why it is very important and very timely for having this symposium here, because we are talking about the type of social impact that NLP research and broader AI research can have and is having in our society. So if these systems were not accurate, people would not be asking about what social good it can make. So we have reached a certain situation where that we have to be talking about these social aspects. So before we go into that, I'll try to express my gratitude towards everybody involved. So we had 6 very inspiring talks yesterday and today, and all a lot of people attended virtually, as well as we had speakers coming in person. So thank you very much for your time and effort. So without your support, this event would not have been possible. And we had almost like 160 plus participants registered in the Eventbrite system, and a lot of people attending virtually yesterday and today. And thank you very much. That makes a real impact of this type of activities. And I'd like to express my gratitude to the Department of Computer Science and the Digital for providing the funding and support for this event. And lastly but not leastly, for Chita and to the customers, without their efforts, none of this would have been possible. So thank you very much. So I've said a lot of good things about NLP and AI in general, but there are also various problematic things. That's why we're having this type of workshop to talk both sides of the problem. So AI has been had certain problems, especially generative models, creating very biased generations from prompts such as CEO. You can't see any like non-white CEO, like non-male white CEOs generated by the system. And if you asked about like nurses, it's generating all like some female nurses. It gets even more worrying when you ask about questions like janitor versus certified firefighter. So you see like white males on your right, and like janitors, you don't see any of these type of people on the left side. And people have certain problems by using these systems for like recruiting, hiring. Luckily, we don't use these type of systems in academic hiring. So at the moment, it's fine, but you have had these type of situations where you get evaluated for your interview performance by AI systems during the interviews, and they do various scoring, and these systems have been shown to be biased for various skin colors and type of responses people are providing, and there have been like a lot of problems. Another severe problem that still continues is fake news generation, fake videos. It just happened like a couple of weeks last week as well. So these things are still problematic, right? So NLP is having a lot of social good as well as a lot of social problems as well. So that's why we need to like keep on continuing this research and these efforts. And NLP is also known to generate a lot of bias and hate speech on the internet. And so it's a lot of like research that has been done in order to address these problems. So, so maybe like when we talk about AI, they're worried about like some superhuman intelligence is going to take over us and cause a lot of like havoc, right? So on more reality, like on more real like existential threats of AI, I get these type of questions from various people. So will we lose our jobs? Right, so because of various new technologies, I don't know like how many people were driven by a autonomous car to this venue, or I don't know like how many people were like having I don't know like say robots to do your washing or laundry at home. I would be worried if somebody does that for me in AI systems. So I'm not worried about like AI systems taking some of these jobs, which I think humans would not have been doing in the first place. So you can still, for example, like say, if you want to drive, then you can drive by yourself if you enjoy that. But if you want to like drive for very long periods of time, maybe autonomous vehicle might be the best thing for you. Just because AI-based generative systems can produce essays or nice pictures for you, doesn't mean people will not be like drawing this, right? Or just because there are like you can play chess or Go or whatever games with the AI, doesn't mean that people don't play these games between humans, right? So it doesn't necessarily mean like just because we have these technologies, we'll have to necessarily lose our jobs. Some of these jobs, I do a lot of like scheduling of emails and things like that. I don't mind if AI can take over that. So, so these type of existential threats. The problem with that is they are actually overlooking the real threats because of these hype ones, right? So there are much more. As I mentioned earlier, like there are much more like readily like encountered threats that we are not looking at because we are like shadowed by these science fiction problems. And another problem that I get asked a lot is that NLP is done as ChatGPT. That's a question like a few minutes ago, like it's outperforming a system, and what you do about this? There's anything else in NLP to do it? So I remember like when I was at NLP last year, just 2 weeks after ChatGPT was released, and everybody in the conference was basically talking about that, right? So, as you see, like there are lots of challenges that needs to be addressed. Even more with these technologies now available. And this is something that I get asked a lot from my PhD students. Like I started on this topic, is it already done now, or what do I do? These are real existential threats for the students, right? Before the AI takes over. So I don't know like good answers to these questions, but like these are the type of questions that we probably need to worry about in the immediate vicinity. So I think as NLP researchers, we are in a kind of a unique situation because we are part of the problem as well as we are part of the solution, right? So if anybody is going to do something about it, that should be us, right? So we have the skill to make these systems safe and productive rather than being threatening things. So we have to, I think first thing to be is we have to be realistic. We have to appreciate the things that the AI systems have brought us. So it doesn't mean that image classification systems have put the radiologists out of the jobs. On the other hand, it has helped a lot of people who don't have access to real doctors to get the immediate medical feedback. If I don't have to wait for the GP for 6 months to get some quick advice, I wouldn't mind that, right? But you have to know that you're getting advice from an AI system, right? So we have to look beyond the hype and realize the real threats. I have to be realistic, right? And you have to be responsible. And if you think there is some probability, a non-zero probability of a risk of something that you are developing, then probably we have to think about how to address it, right? So there's work to be done rather than getting like panicked. So, and I think we have to be optimistic. We have to look at the positive side of AI as well, what it's going to bring us before it's going to extinct us. So we have to work on that. And you don't know, I mean, we might get extinct anyway, right? There might be that asteroid hitting us, or a pandemic, or that nuclear bomb put by some dictator. It can happen anyway, right? So why worry about something that's going to happen anyway? So with that, I think I mean, I've also mentioned that a lot of work has been done in this like field. Unlike humans, AI learn. Right? I mean, look at history, humans don't learn. They make same mistakes again and again. Whereas, for example, this was ChatGPT. We had asked this question in end of last year. I mean, you ask how to classify the scientists based on this type of racial and gender responses, because coming up with actual functions. If you are white male, then you are a scientist, other than that, you are not. But things have improved a lot, right? And this is like last month. And it's generating much more fair and good response, right? Within 2 months' time. So things have improved a lot. And even those dark images that I showed, if you try to generate them, they won't be generated. Right. So that's like a few months' time. So that's why I'm saying we have to be more optimistic about this field and the developments. And as this guy used to say, with great power comes a lot of responsibility. So as NLP researchers, we have to be responsible and hopefully realize more of social good of the type of things that we do. But thank you very much for your attendance.
With this, I think we'll conclude the symposium. But before that, I'll ask all the virtual attendees to please switch on their video so that we can take a group picture all together with the physical and the virtual attendees. Yes, I would request all the virtual attendees to please switch on their videos if possible. And we can all stand over here with the yeah. I would request all the virtual attendees to please switch on their videos, if that's possible. And who is going to take the picture? Someone needs to take it here. So, please, if that's possible, I would request all the virtual attendees to please switch on their videos. Thank you. You have to adjust the camera.
Yeah,
he has adjusted, and we can take the picture from basically there and with the screen.
right.
We all standing over here. Yeah,
Yeah,
so it will come, everything will come.
So two pictures will be taken.
Yes,
and
yes,
one will
yes.
go.
Yeah.
Also,
Yes, I think that's. Could you all please switch on the videos? Yeah, thank you. All the virtual attendees are requested to switch on their videos, please. Thank you. If that's possible, yeah.
No. That camera, yeah. I will.
Could you just see, look into your cameras? That's it, yeah.
We don't need to. Yeah. Okay. Yeah, I think I can. Yeah.
And can you see if there is a set out the picture? Yeah, okay. The whole. Did that come to the screen?
Yes.
Thank you. With this, we'll conclude the symposium. Thank you everyone for joining. And the recordings will be made available very soon to all the attendees through a stream, maybe YouTube. Thank you all for joining. It was nice having all of you. Thanks a lot. We'll end the meeting now. Thank you.